Now here, this is your common collector configuration circuit. Now here, in the case of common collector configuration, the collector is connected to the ground. The collector is connected to the ground, whereas input is base, output is emitter, and because of this, input current is base current and output current is emitter current, and input voltage is between base and collector, it is VBC, and output voltage is between emitter and collector, it is VC. These are your input voltage, input current, output voltage, output current in the case of common collector configuration. Okay. Now, see here, this is your common collector configuration circuit when it is connected to the NPN transistor, as well as when it is connected to the PNP transistor. Okay. Already I discussed this circuit connection in my previous class. See here, emitter junction is always forward bias, collector junction is always reverse bias. See here, this N terminal is connected to the negative of your battery, so this is connected in forward bias. Here, this P terminal is connected to the negative of your battery, so it is connected in reverse bias. So collector is connected in reverse bias, emitter is connected in forward bias. So this is its active region. Okay, and VBB is your supply voltage at input side. VEE is your supply voltage at output side. VCB input voltage across the transistor. IB current to the transistor at input side. And here VCE output voltage across the transistor. And IE is your output current to the transistor. Okay, these are your input output voltages and currents. Okay, now again I'm writing the input equation as well as output equation similar to your common base common emitter configuration. See here, in this case the current is flowing in the clockwise direction. See here, positive to negative, the current is flowing from positive to negative in clockwise direction. Okay, in this case VBB is your voltage, right, whereas RB, voltage across RB, and voltage across transistor are the voltage drops. By KVL statement, VBB is equal to the algebraic sum of the voltage rises is equal to the algebraic sum of the voltage drops. From that, VBB is equal to the IBRB plus VCB. Here, voltage rise is equal to the sum of the voltage drops. Okay. From this input equation, I am writing the input current as well as input voltage here. Input current is given by IB is given by VBB minus VBE by RB. This is the input current. Now from this input voltage is given by VBC is equal to VBB minus IB RB. So this is equation 1 and equation 2. Similarly, I am writing the output loop equation. Now here, I am assuming the current direction in the anti-clockwise direction from positive to negative. Here VEE is your voltage rise, VCE and IGRE are the voltage drops. So that's why it is VEE is equal to the IGRE minus VEC. But here the VEC is connected in opposite direction. Why? Because see here the current is traveling in the anti-clockwise direction, but VCE terminals are this emitter is positive, collector is negative. Why? Because collector connected to ground now. This is lower voltage now. So this is positive, this is negative. But here the current is in reverse direction. So that's why here VCE is negative. Okay, voltage rise is equal to the voltage drop. So you have to note this point, very, very important. Why? Because the VCE is opposite direction when related to this current direction. So that's why we are taking it as negative. VC as negative. Okay. From this equation, again I am writing the current equation, output current equation. IE is given by VEE plus VCE by RE. Similarly, I am writing the output voltage equation. Here, VCE is given by IERE minus VEE. Now this is equation 10, equation 4. Okay. In addition to these 4 equations, I am writing one more equation, that is output current in terms of reverse saturation current. Here, IE. Already I discussed this equation in my previous class. That is, output current is equal to the gain into input current plus 1 plus gain into reverse saturation current. So here, output current is given by IE in the case of common collector configuration. Output current is IE, and here we are going to represent the gain with gamma. Gain with gamma. So output current is equal to the gain into input current. Input current for this is IB. So IB plus 1 plus gain. Gain means gamma into reverse saturation current IC naught. Okay. Now, instead of writing 1 plus gamma into IC naught, I am writing it as ICEO, nothing but IECO. See here, IE is equal to gamma into IB plus IECO. Here E indicates the output current. E indicates the output current. Now here in the case of common conductor configuration, what is the output current? It is emitter current. So that's why it is E, emitter current. Here what is meant by C? C indicates the terminal connected to ground. So here the collector is connected to ground. So it is connected to ground. Okay. And after this 0 indicates the reverse saturation current. So in some textbook he is going to mention like this. That is IE is equal to gamma into IB plus 1 plus IECO. Where ICEO is given by, or IECO is given by 1 plus gamma into IC naught. Okay, these are your input current, input voltage, output current by seeing this circuit diagram. Okay. Now, from this, here I written these key points. You have to read these key points. Okay. Now, from this, I'm going to explain this input as well as output characteristics of your common cluster configuration. Okay. Now see here. Okay. Here this topic is related to common collector input characteristics. Okay. Now here this base end, this is connected reverse bias, this is connected forward bias. Here the base is having the members here. We have 0.7. Like 2 minus 0.7 will become 1.3. So that's why the top is going to increase from this IUC.
Sir, your voice is breaking.
Voice is not clear, sir.
Okay. From 4 volts to the 2.7 volts. This is your input graph. Input graph is drawn between the input voltage VCB versus input current IB. So here input voltage is VCB in terms of volts. Input current IB is in terms of microamps. You have to remember this point. IB is in terms of microamps. Whereas the IB is very, very less value when compared to the IA and IC. So that's why I'm going to take IB as in terms of microamps. Okay. Now see the output characteristics of your common cluster configuration. Now here, to explain this output graph, I am taking the output current in terms of reverse saturation current. See here, IE is equal to gamma into IB plus 1 plus gamma into IC naught. This is I explained in my just a few minutes back. I explained this output current. Now see here, whenever IB is equal to 0 microamps and gamma is equal to 55, then what will happen to this equation without this IC naught? Without this IC naught, I am not applying any output voltage. That means I am not applying this VGE. If I am not going to apply this VGE, then what will happen? Here, there is no IC naught. If you not apply, there is no IC naught. Now this equation will become IE is equal to gamma into IB. Here I am assuming that IB is equal to 0. Here, initial I am assuming IB is equal to 0. If IB is equal to 0, then what will happen to IE? IE will become 0. IE is equal to 0 without this reverse saturation current. Similar to your common emitter configuration. Expression is similar to your common emitter configuration. See here, IE is equal to 55 into 0. It will become IE is equal to 0 without this and without this reverse saturation current. I am not considering this initially. I am not considering this reverse saturation current. It will become only IE is equal to gamma into IB. It will become IE is equal to 0. Now I am considering this reverse saturation current. That means when you increase the supply voltage at output side, when you increase the supply voltage at output side, sorry, this is not VCC and this is VGE. This is not VCC and this is VGE. This is VGE. Once again, I am writing this. Okay, now here. When you increase the VGE, okay, when you increase the output supply VGE, because of that output voltage is going to increase here. When you increase the supply voltage, because of that output current at transistor, output voltage across the transistor also going to increases. If the output voltage increases, then the reverse saturation current also going to increases. That means here the output current IE is going to increase from this 0 milliamps to the remaining value. Okay, see here. IE is going to increase from 0 milliamps to the remaining value. Okay. Similarly, when you apply 10 microamps, when you apply the input current IB is equal to 10 microamps. Now I'm going to apply the IB is equal to 10 microamps here. I didn't written that 10, so I will explain 20 otherwise here. In the case of 20, when you apply this 20 microamps, now what will happen here? 20 into 55 from this equation. IE is equal to 20 into, that means I am not considering this equation again. If you consider this equation, if you consider IE is equal to gamma into IB, it will become 55. Gamma is already 55. IB is equal to 20. So 20 into 55, it will become 1.1 milliamp. If you calculate this value, it will become 1.1 milliamp. Why? Because IB is in terms of microamps, and you have to remember that point. 55 into 20 into 10 power minus 6. If you calculate that value, you are going to get this IE value as 1.5 milliamps. Okay, that means without reverse saturation current, this is going to increase up to 1.1 milliamp. Okay, now I am considering this reverse saturation current. That means when you increase this output voltage across the supply, because of that output voltage across the transistor is going to increase, as well as the reverse saturation current also going to increase. Because of this, what will happen? IE increases from 1.1 milliamps to the remaining value. Okay. Similarly, I am going to apply this current at 40 microamps. Now this will become 40 into 55. It will become 2.2 milliamps. Okay. Now again consider this reverse saturation current. Now when it is going to increase, and when you increase the supply voltage VEE, because of that VCE increases, and because of that reverse saturation current is going to increases. Okay. One second. Now, when IB is equal to 40 microamps, because of that IE is equal to 2.2 milliamps without IC naught. Okay. When you consider IC naught, when you increase supply voltage, because of that output voltage across the transistor is going to increases. Because of that reverse saturation current is going to increases. That means output current IE increases from 2.2 milliamps to the remaining value like this. Here, it is going to increase from 2.2 milliamps to the remaining value. Okay. This is a output characteristics for common emitter configuration, Okay. Now see this input impedance, output impedance, current gain, voltage gain, bandwidth in this case. Okay. Now input impedance is given by input voltage by the input current. Here input voltage is VBC, input current is IB. Here IB is in terms of microamps now. So here the denominator is less value. It will become, total value will become high value. Okay. And output impedance is defined as ratio of output voltage VCE to the output current IE. Output voltage VCE to the output current IE. Here IE is milliamps now, so output impedance is going to low value when compared to this. When compared to this value is low. Okay. And if you see the current gain, it is ratio of output current to the input current. That means IE by IB. Here IB is in terms of microamps, so this total value will become very high value. Okay. And after voltage gain, that is output voltage to the input voltage. This is unity, whereas bandwidth is high. Okay, this is a